Hey guys, this is lesson 6.3. We're going to work on a few problems that require us to convert from moles to grams, as well as deal with what's called percent yield or ending percent, okay? So I'm just going to do a series of problems and we will do a lot of practice problems in class when you guys come in, okay? So percent mass of elements. How are we going to use what we know to solve these different problems? Okay, I'm going to be using the iPad at the same time. Okay, so we have this chemical reaction, B plus S2 gives us B2S3. Okay, we want to answer the question, if 2.5 moles of boron are burned in sulfur gas, how many grams of boron sulfide would form? We have boron, sulfur, boron, sulfide. So the first thing we want to do is we want to balance this equation. Okay, so I have two borons on this side, which means I need two borons here. Now I have two sulfurs here, three sulfurs here. So I need to find a common factor between both of these. So if I put a 2 here and a 3 here, is our equation balanced? No, because we need to fix the number of borons on our initial. Now our equation's balanced. 4 borons plus 3 sulfurs gives us 2 boron sulfide. Okay. So if 2.5 moles of boron are burned in sulfur gas, how many grams of boron sulfide would form? Now, it's really important that we realize that this balance equation gives us some more information to work with. This says that we have 4 moles of boron, 3 moles of S2, and 2 moles of B2S3. So we're going to use stoichiometry in order to do this. Okay, so what we're given is we're given 2.5 moles of boron. And it wants us to say how many grams of boron sulfide we have. So the way we're going to do this is we're going to convert boron to boron sulfide using stoichiometry. And then we'll have that in moles and we'll be able to convert to grams pretty easily. So this says for every 4 moles of boron, we have 2 moles of boron sulfide. Let me erase this. Okay. So now our moles of boron cancel and we're left with moles of boron sulfide, but we need grams of boron sulfide. So we're going to go ahead and say that 1 mole of boron sulfide equals the molar mass, which is 117.83 grams boron sulfide. And again, I got this from the periodic table. I just added 2 times the molar mass of boron and 3 times the molar mass of sulfur. Okay. So if we do this calculation down here, 12.5 times 2/4 times 117.83, we will get around 736 grams of B2S3. Okay. Converting from moles of one substance in our reaction to grams of another substance. We got to do this stoichiometric conversion here that we got from the equation above. Okay, so again, I'm going to balance the equation. We have 4, 3, 2. How many moles of sulfur are needed to react with 7.5 moles of boron? So we're given 7.5 moles of boron. We want to know how many moles of sulfur are needed to react with this. So again, we can look at our equation and say for every 4 moles of boron, we know we need 3 moles of S2. And if we do this equation here, we will get 5.6 moles of S2. Okay, again, using the equation, using the stoichiometric values, using the molar ratio, we can get from moles of boron to moles of sulfur. All right, again, let's balance the equation. 4, 3, 2. How many moles of sulfur are needed to react with 100 grams of boron? So earlier we went from moles to moles. Now we want to add this idea of mass beforehand. Okay, so we need to go start with what we're given, 100 grams of boron. We want to convert grams to moles, and we can do that using the molar mass. So 1 mole of boron is 10.81 grams of boron. And now we want to convert moles of boron to moles of sulfur. And we can do that by using this ratio here. So 4 moles of boron and 3 moles of sulfur will give us around 6.938, again, staying consistent with my sig figs. Okay. So again, this is very dimensional analysis, but we are, understanding what we have and how the process works in order to get what we need. Okay. And a lot of the times you're going to convert between grams to moles, use that stoichiometric allowance that we have using the chemical reaction to convert between moles of one substance to moles of another substance. Okay. We'll do a couple more. How many grams of boron burned if 2.00 times 10 to the third grams of boron sulfide formed? Okay, so we want to go from grams of boron sulfide to grams of boron. How are we going to do this? Well, first, we want to convert this to moles. Then we want to convert the moles of boron to moles of B2S3. I'm sorry, forget what I said earlier. We want to convert the grams of B2S3 to moles of B2S3. We want to convert those moles of B2S3 to moles of boron. And then from moles, we can go to grams. And I'm going to break this down for you. Okay, so we have 2.00 times 10 to the third grams of B2S3. 1 mole of B2S3 is equal to the molar mass, which is 117.83. Again, this is just the atomic mass of these, but in grams, added up together. And then we want to say, well, our balanced equation gives us so much information that we can work with. We have, for every 4 moles of boron, we have 2 moles of B2S3. So 2 moles of B2S3 is equal to 4 moles of boron. And then we know for every 1 mole of boron, if we look at the periodic table, that equals 10.81 grams of boron. So if we do all this out, 2.00 times 10 to the third divided by 117.83 grams of B2S3 times 4/2 times 10.81, we will get an answer that says it is 3.67 times 10 to the third grams of boron. And again, just staying consistent with that first value in terms of significant figures. And then our last problem here is going to be a little bit different because it's going to include some kind of percent yield, and how we go to that percent yield is going to be really important. So again, I'm going to balance the equation. If 10 grams of boron is burned in a reaction and 56 grams of boron sulfide is produced, what is the percent yield? So this is basically saying that you were in the lab and you burned 10 grams of boron in this reaction. And you basically, your output is that you got 56.00 grams of boron sulfide. So this is what you got in the lab. This is going to be known as the theoretical value. Okay. And when we do the stoichiometry, we're going to get an actual value. Okay. And then we can compare the theoretical value and the actual value to get a percent yield. So what we got is what we got in the lab. There is a true value or an actual value that we're going to solve for right now. So again, we're going from 10 grams of boron. We want to convert the 10 grams to moles. We want to convert the moles of boron to moles of B2S3. And then from here, we can say, well, 1 mole of B2S3 is equal to 117.83 grams of B2S3. Okay. So we're going to get an actual value of 54.50 grams. So obviously our experiment did not go well because we got 56 and we were supposed to get 54 grams by the laws of stoichiometry. So something went wrong in our experiment, but that's okay because we can solve for a percent error and see how much we actually got correct. And the way we do this is we use the equation actual over theoretical times 100%. And I'm going to move this up here and say, well, the actual value is 54.50, and we got 56.00 in the lab. We can multiply all this by 100%, and we should get around 97 sig figs. Around 97.3%. Okay. We're going to do a lot of examples on this. We're going to do one very, very similar to what we just did now. I encourage you to rewatch the video, or at least go to the parts where you can see these solved. Put them down. There is no questions on formative, just to upload your notes. To upload, make sure that you went through this and you understand. Okay, take care.